Hey, today on Flipping Science we're looking at clay silicates, acid rain and water softening. So we're going to look at how cations are held on the surface of soil silicates and how those are made available to plants. I'm going to describe the effect of acid rain on releasing cations from soil silicates, which we've already kind of looked at before, and explain how silicates are used in water softeners. So clays make up a decent amount of soil. Soils are formed from the breakdown of rocks, so weathering and erosion of rocks. Those rocks can be silicates or luminosilicates, and if they are, then you get particular characteristics of the soils. So some clays have a three-layer structure, and that leads to a negative charge being present on the surface. So on that negative charges that you have on the surfaces of the clay, you can get positive ions like potassium, sodium, calcium, magnesium, ammonium and hydrogen. All those ions can stick to the negative surface through electrostatic attraction. So in our picture here we've got a clay, the clay has a negative charge, we've got these positive charges sticking to it. If we look over here, so here we have aluminium and oxide, so there'd be silicon in there too, obviously, if it's luminosilicate. So where these oxide bits are to it, they have a negative charge. So those negative charges there can attract positive ions. So here we've got potassiums, we've got calciums, we've got magnesium. So they're being attracted to the negative charge of the clay. This is important because plants can use these ions from the clay. So if there's a lot of water in the clay, the plants uptake the ions from the surface of the soil, so the plants can absorb those ions, and that's important. So this is important, it's called ion exchange. So there's a continuous movement between ions in the soil and going into plants and the soil water. So if we look at the clay, here we've got some potassium ions that are stuck to the clay. In water we've got some calcium ions, so that's in the soil water. The calcium ions can replace the potassium ions on the clay. The potassium ions go into solution, then they could be absorbed by the plant. Remember, plants can only absorb nutrients if they're in a soluble form. So if they're stuck to the clay, they can't use it, but if it's in a soluble form in the soil water, then they can absorb it. So, and that's again what this picture down here is showing. We've got the calcium attached to the clay. Here instead though, we've got some hydrogen ions that are sticking to the surface of the clay. And this is important when we look at acid rain. So in acid rain, you can get that equilibrium between the metal ions that are stuck to the surface of the clay. So here we have metals stuck to the clay, and hydrogen ions in the soil water. So here's some hydrogen ions in the soil water. So the hydrogen ions, if we have a look at our little diagram down here, here's our clay with the surface negative charge representing the yellow. We've got some positive metal ions. We flush this through with acid rain, and we get hydrogen ions replacing some of those positive metal ions, and those positive metal ions are going into the soil water. This could be good, they could be absorbed by the plants, but it could also be bad if we have toxic metal ions like aluminium being released. So aluminium is toxic to plants. If aluminium goes into the soil water, then it can be absorbed by the plants. So like I was saying, this can be helpful because plants need magnesium, calcium and potassium to grow. But aluminium ions are quite toxic, so if they're released, they'll leach into the soil. This is leaching, and that can cause a hassle to plants, but also that water can be flushed down into rivers and streams, and that can lead to aluminium ions building up in lakes and streams, and that can be quite bad for the organisms in there. Now we're going to talk about cation exchange and zeolites, zeolites and ion exchange resins. If you're in a place that has soft water has very low concentrations of calcium and magnesium ions. So if you chuck some bubble bath in a bath, you'll get lots and lots of bubbles. If you live in a place with hard water, you'll get very few bubbles being produced. And that's because of how the calcium and magnesium ions interact with the detergents. So just restating that, hard water has large concentrations of calcium and magnesium ions. And where I live in Adelaide, we have very hard water because of where our water comes from. Our water comes mainly from a big river that has big limestone cliffs, so you get limestone dissolving into the water. And limestone is calcium carbonate. Zeolites are naturally or synthetically occurring silicate or luminosilicate structures that have a very open and stable honeycomb structure. So this open, stable structure, it means that you get these holes, you can get pores and tunnels and cavities, and because it's made of silicates and luminosilicates, there's a negative surface charge in there. So it means it has a really large surface area, it's solid because it's silicate, and water can flow through it really easily. So large surface area, big negative charge, solid, water can flow through it. So what can happen is you get an ion exchange between water that's hard, so you can get calcium magnesium ions sticking to the surface of the zeolite. So we can use these zeolites or ion exchange resins to soften water, and by that I mean remove the calcium and magnesium ions. So we have a look at this picture. We've got these big circles, that's the ion exchange material, so the zeolites or the ion exchange resin. The water coming in is big in calcium ions, which are the triangles, and magnesium ions, which are the squares, so it has a high concentration of those. As it's flowing past this ion exchange material, we're replacing the ions that are sticking to the surface of the ion exchange material with other ions. So here you can see the calcium magnesium being attracted to the negative surface of these circles. Now, like I said, the structures aren't circles, they're those big porous honeycomb networks that I saw on the previous slide. As the calcium magnesium ions stick to the ion exchange material, the other ions that are present there, the sodium ions in this case, they come out. Now, the reason why there's sodium ions there is you flush these things with salt water to recharge them, and I'll talk about that in the next slide. So here's a picture of a water softener. So you have hard water coming in. Here it says plastic beads, that's the ion exchange resin, so that's the synthetic one. The water flows through and you get that ion exchange happening. And then on this other side, you have this brine tank with really salty water. What happens is once you've had some water that's gone through and is being softened, you then recharge the plastic beads with salt water. And let's have a look at how that works. So we're using M as calcium and magnesium ions. So on the surface of the zeolite, we have those sodium ions that we start with. We flush through the calcium and magnesium ions that are present in the hard water in large concentrations. And the calcium and magnesium ions, they stick to the surface of the zeolite and sodium ions get released. So that's called softening because you're removing the calcium and magnesium ions from the water. You can then recharge by flushing through salt water. So you're going back in the other direction. So you're getting rid of the calcium and magnesium ions, you're just draining those away so they can go somewhere else. And you're replacing them with sodium ions from the salt water. So then you can reuse the ion exchange material again and again, as long as you keep on reflushing it with the salt water every now and then. And you use highly concentrated salt water because then you're going to get a lot of exchange really, really quickly. So back here on the slide, you can see that they use a brine tank. Brine is really, really concentrated salt water. So this goes back in, reflushes over the beads, and then you flush in your hard water to produce the salt water. Here's a picture of some of those zeolite structures. So again, we've got this open honeycomb structure. We've got the sodium ions on the surface here. As the water goes through, you replace those sodium ions with the calcium or magnesium ions. And that's shown in this diagram here. So again, you have the zeolite here. You flush the water through with magnesium ions. The magnesium ions get stuck to the internal surface of the zeolite. And then you could flush that back through with salt water to regenerate it. So let's have a look at some questions. So this question here, it talks about chromium ions being removed from water using a zeolite column. Chromium will work the same as calcium or magnesium. It's a metal ion, so it'll have a positive charge. The question says, state two characteristics of the zeolite structure that make it effective in removing chromium ions from large volumes of water. So there's many things that we can consider here. The zeolites are porous, so they have those holes so the water can flow through them. As the water flows through, it can deposit the calcium and magnesium ions, or in this case, chromium ions, on the surface of the zeolite. Zeolite also has a large surface area, so there's a large surface area for that exchange to occur over. There's lots of opportunity for chromium ions to replace other positive ions on the surface of the zeolite. It's solid, so it doesn't dissolve in water, so that's a plus. And the main thing really is there's a negative surface charge on the zeolite. So the zeolite has a negative surface charge, so electrostatic attraction can occur between the chromium ions and the zeolite. The second question is asking about aluminium ions and soil water. So it says, state how acidic water in soil causes the mobilization of aluminium ions from clay surfaces. So what you'd be talking about here is aluminium ions exchanged with hydrogen ions from the acidic water. So you don't really even need to explain this because it's a state, but you're going to get ion exchange between the hydrogen ions from the acid and the aluminium ions from the clay surface. So the hydrogen ions from the acid replace the aluminium ions on the clay surface. The aluminium ions go into the soil water. The acidic ions get stuck to the surface of the clay. So that's the idea there. So today on Flipping Science, we looked at acid rain, soil silicates, and ion exchange resins and zeolites. That's it for Flipping Science today. See ya.